So, happy to introduce Professor Mari Bukowski, and then who is the director of the School of Design, Art and Design currently. And then he's speaking about the art and the mathematics instinct and the relation between the mathematics and art. Please welcome Mari.
To thank Dr. Achenbach, the Dean of the College of Science, for helping arrange this, and also Professor Choi, who did a lot of the work to organize this to make it happen. So thank you very much. I appreciate it. And thank all of you for coming. I'm sure most of you have better things to do on a Thursday afternoon, so I appreciate you coming. I wanted to talk a little bit about the work I do because I am highly influenced by mathematics, which frightens a lot of people when I tell them that, because it's not something that people commonly think go hand in hand. But just to give you a little bit of a background of myself and how my interest in math and art came to be, since they seem to be kind of disparate fields of endeavor, how they actually do come together and relate to me. So my father is a retired mechanical engineer and my mother is an artist. So I had a mathematical influence from my father's side and artistic influence from my mother's side. And my parents were very practical people, and I think that they wanted both of their children, my brother and I, to go into mathematics because it was a very practical field. They knew that we would be employed well, and I can say my parents are very proud because my brother is a mathematician. So they do have one child they are very proud of. But I actually did follow their strict encouragement to apply to go to college as a math major, and I got into all 5 schools as a math major, and at the last minute I thought, I wonder how happy I would be doing that. I like math and I'm good at math, but I wasn't sure that that was really the best track to go on. If I became a mathematician, how would I be able to include art in my work? But I could see if I became an artist, how I could include math in my work. So at the last minute, I applied to art school, got in and turned down a scholarship to MIT so I could pursue a career in art. So my parents were devastated, but at any rate, I went ahead and pursued art much to their dislike. But I think they've gotten over it by then. So it took me a while before I could figure out exactly how to relate. I had this strong interest in math, but how do I relate it to what I'm really passionate about in art making? So one of the first things that I became interested in were these 2 equations. Brian, this is for you. You have to solve this by the time that the lecture is over. I saved it for you. You got an hour. So I became interested in these 2 equations. If you look at them, even without knowing what they mean and what the actual equation is, you can see they look very similar. Well, in the 1890s, Joseph Boussinesq was working on experiments where he was dealing with water waves, water in a very shallow canal, shallow and narrow canal, and measuring the surface of the waves of the water. And based on his experiments, that was the equation that he came up with. And so it wasn't until the 1950s when Enrique Fermi, along with John Pasta and Stanislaw Oolong, physicists, got together, and they were performing experiments as well. But they were doing completely different experiments. They were experimenting with an oscillated beaded chain, basically. And they were finding that based on the oscillations they were getting on that chain, they were getting very similar results to the Boussinesq equation using water waves. So completely different experiments, but they were getting very similar results. And so once their findings were published, mathematicians after that, for a long time, thought, since those equations look the same, they certainly must be equal to each other. But nobody could actually prove that. And in 1997, my brother proved that as part of his PhD thesis. So So these two equations actually do equal each other, and it's known as the Boussinesq limit of the Fermi and Pasta Ulam equation. And so I was actually very involved in his thesis because a lot of the research he had to do to prove these equations, he was finding documents in German that he would have to translate. I happen to speak fluent German, so he would send me these documents in the mail. This was well before email was quite as popular as it was. He would send me these documents in German, and I would translate them in English, and I would send them back to him. And this went on for 6 years, so I felt like I really had a full understanding of what was going on, what he was trying to do with this equation, or these two equations, to bring them together. And I became really interested in just the beauty of the math itself and the patterning in that. And so I decided that I wanted to make a book based on that particular equation. So I started working on these really small 6x6 inch prints. And at the beginning, you can see that I was actually incorporating parts of the equation into the prints. And it seemed that it was off-putting to people, because if you're not a mathematician, or even if you are a mathematician, but you're seeing this out of context, didn't necessarily make sense. So I started to simplify some of the imagery in the work, and just trying to use symbols that would allude to certain things, these patterns, these movements that were happening in these equations. And so as I made my way through, I tried to simplify and try to find things that could engage the viewer. So over about a 2-year period of time I was working on these prints, I ended up with about 500 of these prints. And at that point, it was too big for me to bind as a book. I didn't really know how I could actually bind them and have it make sense as a book. And I was happier with the later images rather than the first images that were so dense with the mathematical equations. But I felt like they were all interrelated, that I couldn't whittle them down, cull out some and put in others to make a book. So I decided that that entire project was a failure, and they're just standalone images that I actually never ended up doing anything with. But it was a really interesting experience to go through that. So after that, I became very interested in the catenary. And I'm sure most of you know what a catenary is. Galileo had hung a chain. He had put 2 nails in a wall, just basic construction, 2 nails in a wall, not necessarily even on the same horizontal line. 2 nails in the wall, hung a chain from it. And the way the chain hangs, it pulls its own weight, so you can't stretch it beyond where it already is. And so because of how it holds its weight, that arc is called a catenary. Well, this was the first time that Galileo had done this and had noticed this. And he believed that he had found the actual arc for a parabola. And then Christian Huygens, who was a Dutch mathematician, said, I don't know what that is, but it's not a parabola. So if you look at these two arcs in this graph, you can see there's a red arc and a blue arc. The red arc is the catenary, the blue arc is the actual parabola. Very indiscernible difference. It doesn't look like there's much difference, but there's a big difference when you consider how they are actually or can be functional. So when you think of a catenary, you think of something like the St. Louis Arch. Or maybe you don't think of that, but maybe you will now. But if you consider the St. Louis Arch, it does not collapse in on itself because it is that catenary. If it were a parabola, it would not be able to hold its own weight. That's what's so interesting about the catenary, is that it maintains its weight. And so even though there's that very indiscernible difference, there is a big difference between them when it comes to that kind of functionality. So I became really intrigued by the subtleties of those two arcs and decided to make a series of prints based on that. So you can see on the right-hand quadrant, there's a number of these arcs or vessel-looking forms that some are parabolas and some are catenaries, and you have to kind of figure out which is which. And over here on the left-hand side, in the back, there are these silhouettes of the forms of the arcs. So you can, if you look closely, you can see a little bit of the patterning of arcs, whether they be the parabolas or the catenaries, and then discerning which is which. Something else that I don't know that I really noticed until I got to this series was I never considered myself a person interested in patterns, but I found that patterns are really intriguing, even if I don't mean for them to be intentional. And so even with drawing all of those circles, patterns start to emerge. And I have the catenaries and the parabolas behind them that come out and emerge as their own pattern. But then the circles themselves start to make patterns, and I found a real intrigue in that. And so I decided to focus on the idea of that patterning, which led me to this. This also leads to the next thing, that I can be maybe a little bit obsessive when it comes to certain kinds of things. There's 38,581 circles in this piece. That number doesn't necessarily matter, but the fact that I count them as I make them and find it to be a very meditative process, it's the process of actually counting them that makes the difference, not the final number itself. So the counting itself doesn't have to conform to a specific number, but the fact that the counting happens is something that's important. And so again, there's patterning that comes from this. And also something that in a strange way you think about nature, the perfection of nature, and thinking about fractals and the iteration that happens with fractals. And the imperfection within perfection. And that's what I like about making artwork by hand. It's not mechanically generated, that's not done on a computer. That everything is hand-drawn. Even if I scan it in later, it starts from just straight hand pencil to paper. So that way I can get things as humanly perfect as possible, but in the end we know that there's no such thing as that. It can't actually be perfect because there's no perfection in the human hand. And so all of these circles were hand-drawn. You can see there's an unevenness to them. Because of that unevenness, they start to generate their own patterns, which I became really interested in. And so when I work on something as tedious as this, I find that I have to do something else to kind of break me away from that tedium, something that's a little bit freer and looser. So I find that I always work on more than one project at a time. I have multiple things going in my studio. So to get away from the idea of being as tedious as this, I moved on to this, which turned out to not be quite as free and as loose as I had anticipated. So this is about 4 by 5.5 feet, and each of the panels is 6 by 8 inches. And this is just straightforward counting, where in the very upper left-hand corner I started at 0 and just wrote numbers, in order, 0, 1, 2, 3, as far as I could get, and just see where the number I got. So this is a detail of the last panel, and you can see what it looks like. And so I ended up getting to 115,574. And again, the number doesn't matter, but it's the counting that becomes important. Again, I'm not trying to count to conform to a specific something. It's just the fact of the counting that becomes meditative. And again, I find that patterns start to come out of this, whether you're thinking specifically of fractals. I notice that the further away you stand from the piece, you don't necessarily know that it's text right away, so it starts to appear like a landscape. You start to notice patterns in it. You start to try to figure out and discern what those patterns are, and it's not until you come closer that you see it's made up of the text. And again, it's that idea of the imperfection within perfection, because you can see where the pen may leak too much ink, so it leaves a darker mark, or where the pen runs out of ink and I have to switch to another one, or where I've just written the wrong number and I've gone over top of it and rewritten the correct number, right over top of it. So you can see all the mistakes and everything that happened in this piece. And so the intention behind this piece was just the idea of counting, the meditation of the counting, and then the patterning that comes through that. And then I moved on to something slightly different. After working that way for a while, where I was just alone in my studio, just left to my own devices, I felt like I was starting to miss the things of working with somebody else, that collaboration that I had with my brother, working back and forth with somebody else to generate ideas and think about things. So I paired up again with another mathematician, and I became very interested in graph theory. And even if you don't know anything about graph theory, you can just guess by the name graph theory that it's naively artistic, because you're dealing with graphs, you're dealing with images. And that's why I always thought math was very easy. Because even if I didn't understand the math itself, if I drew it out and I could see it, it made perfect sense. And so it was that kind of logic that really got me involved in mathematics and how the imagery in my artwork really starts to come out. So I actually, for this next project, became focused on the Königsberg Bridge problem. And that actually is the very first theory in graph theory. And it's based on the idea of the city of Königsberg. And the question is, they have this river that runs through the city with 7 bridges that take you to different parts of the city. And the question is, can you start at one point, cross over each bridge only once to get back to the beginning? And the answer is no, you can't do it. But it was the first theory that really involved mathematics and graph that really launched graph theory to where it was. So I made a series of artwork that became basically a mathematical equation, where I started with that basic idea in mind, that basic grid in mind. And I started to take those forms and more or less collage with them on a 2-dimensional plane. And so the idea of the book came back to me at this point. Now these are large prints, these are almost 4 feet in size, so they're not what you would consider a traditional book. But I started to become interested in the idea of a book at this point because I was thinking of these graphs and the mark making in order to make the graphs. And this whole series of artwork, from moving from one point, if you go from this print to this one, if you look in the very center of that piece, you can see where those 3 circles used to overlap. You can see the halos of them in that very center of that piece. And so what I ended up doing here was every time I would ink up a plate and run it through a press, and I would come out with a piece of artwork, I wouldn't clean the plate again. I would ink it up again, and I would run it through the press again. So I would have a new image, but with the new image, I would have the added residue from the previous image. So I started to think of that as a book, where when you get to the end of the page on one, it continues on the other. So I felt like it was that sort of continuation from the first print to the second print to the third print to the fourth print. So it was very important to me that they actually be viewed in the order that they were pulled in. So usually if you're editioning artwork where it's the same piece, it's the same print over and over again, it doesn't necessarily matter the order that they're in. But this, to me, made sense that they had to be viewed in the order that they were hand-pulled, because that showed that logical sequence. So every time I made an actual piece, an actual print, it was almost like solving another mathematical equation, because I had to consider the space that it took up in the first one. Then I had to consider the next space that I was making. So even though these are 2-dimensional prints, just ink on paper, I was starting to really think about them in 3 dimensions, as though they had an X, Y, and Z axis, because I was considering that the back of that picture plane would drop out and that space would become deeper. And in between the residue from that first image to the actual printed image of that second one, there was something happening in between that, even though it was all on that same surface. So after that, I moved on to another series, the Catalyst series, where I started to think about a lot of different things. This was about the point where I think I came to my midlife art crisis and decided that I really needed to do something different. I think after that last series, I felt like the making of the artwork just became very easy, and the process became very easy, and I think the images were starting to look the same after a while. So I wanted to do things that were a little bit different. It was at that time that I became interested in the 5 most important symbols in mathematics. So you have 1, 0, pi, the imaginary number e, and I. And you know, 0 and 1, those are the most common ones. We know that those are the additive and multiplicative identities. And then pi, we know what pi is. And then E and I are a little bit more complex, but they're very interesting. And so I started just reading more about them and just becoming pretty engaged in equations that involve those numbers. And there is one equation that actually has all 5 of those numbers in them, which I found to be pretty fascinating, was Euler's identity, named after Leonard Euler. And the Benjamin Pierce was a mathematician and philosopher at Harvard, and he actually proved that during a presentation one day. And it was really interesting because he said, we cannot understand the formula and we don't know what it means, but we've proved it, and therefore we know it must be the truth. And there was something about that that I just found to be really funny, that he didn't even necessarily know what it meant, but that it's proven that has to be what it is. So thinking about all of these things, I was starting to think about how could I reconsider my artwork and do something a little bit different with it, where I had to engage in it in a completely different way. So I started using processes that I either didn't like, processes that I didn't think I was good at, and then all the things that I was comfortable with using in the studio, I eliminated all of those things. So that way things wouldn't be that predictable for me anymore. And then it would be that challenge of figuring out Euler's identity. How do you actually solve it? So I kind of went through my own sort of mental process of doing that by making artwork. And again, this is just a basic graph of a pendulum. I started thinking about ideal pendulums and regular pendulums. That had been something that fascinated me. Again, I never really got away from the idea of patterning. You can see it's got the imaginary number I in it. But there was something that I found really engaging about comparing those pendulums and how those patterns worked. So if you consider a regular pendulum and it swings, if it swings back and forth, it's eventually going to swing less and less until it comes to a stop. Well, if you graph that out, it's going to graph like a spiral. If you have an ideal pendulum, it's going to keep swinging, and it's going to swing to its fullest point and never stop. So if you graph that out, it comes back and graphs to a full circle. And so images like that gets me thinking of the differences between the pendulums, the 2 pendulums that I was just talking about. And again, I've been talking about fractals, but the idea of that iteration and the reiteration over and over again, repetition and patterning. And so I was thinking about all of these things while I was making this work. I was thinking about pi and fractals and just the repetition. And so, you know, in the upper right-hand corner of that piece, I had taken out pi to 1,000 places. Because why not? It's those kinds of things. Again, it's about the meditative quality of doing that, and it's the idea again of not necessarily counting to conform to anything specifically, but just the idea of counting itself. And just the tedious quality of repeating things over and over again. You can see there's a graph for a pendulum. You can even see a swinging pendulum in the background here on the far right-hand side, just the instances where it would fall on a graph. And again here, same kind of thing, and I'm thinking about where things are in space. Again, if you've got the residue of the previous print and you've got the ink from the newest print, what's happening in that space in between? So then I start to think about spaces in between and measuring that space, even though it's only a 2-dimensional surface. So I'm still thinking in 3 dimensions, even though there's only 2 dimensions that are actually visible. And I found that the more tedious the work becomes, the more interested I am in it. And so in 2010, I was really fortunate. This was at the previous institution where I taught at Louisiana Tech University. They had an Institute for Micromanufacturing, and it was housed within the College of Engineering and Science. They decided in January of 2010, for the first time, they were going to do a fellowship. And they were going to do a call out for faculty to all faculty who were not involved in the College of Engineering and Science. And they wanted to bring in one faculty member who was in a completely different field, with the hopes that they would be able to engage with engineers and scientists in a different way that engineers engaged with each other, or scientists engage with each other, with the hopes that it would generate new ideas and kind of advance the interest in both disciplines, whatever those disciplines were. And I thought, well, this is a great opportunity. This is exactly what I love to do. And so I applied for it, and I became the first faculty fellow. So it was a 6-month position. It came with a stipend. And the only drawback to the fellowship was that it was only 6 months. I asked for it to be extended to a year, and they said no. And so when they said no, I asked if I could be the permanent faculty fellow, and they said no. And so they wanted to be able to rotate faculty through and have a variety and diversity of things, so that was understandable. But while I was there during that 6 months, I had access to absolutely anything and everything I wanted. I had keys and fobs to every facility that they had. All the microscopes I had free use to. And so I started working with one of the chemists in the Institute for Micromanufacturing, who was doing layer-by-layer nano assembly at that time. And he was really interested. He was working with a chemotherapeutic solution to fight cancer. And what he was doing was putting chemotherapy into these nanocapsules, so really small capsules, that would be injected into the bloodstream. So they go directly to the cancerous cells. So that way they don't actually kill the good cells, they just kill the bad cells. And so his work was focused on cancer treatment. But what was interesting about the layer-by-layer assembly was that it reminded me a lot about printmaking. Because there's this adsorptive process where you're alternating positive and negative atoms and ions on the surface of these substrates. And so you run positive ones across, you soak them onto that plate, let them adhere, rinse off the excess, and then you add the negative charged ones. Rinse off the excess, certain ones adhere, then you put the positive ones on. And so you build up this plate, so to speak, much like printmaking. So I felt like there was this real interesting similarity between that layer-by-layer nano assembly and what I was doing as a printmaker in the artist studio. And so these were some of the images taken. What I found really interesting about these images was that these were taken on the scanning electron microscope. And they start to look like they could be just these massive images or massive things, where they could be the surface of the moon. So I like the idea of something that appears like it could be micro or macro, not knowing the scale of it, whether it's something really large or really big, and it makes you consider where you are in relation to that space. And so I started to do a number of pieces. They had this long corridor that connected the IFM to that biomedical building. And it was just this long sterile hallway with absolutely nothing in it. So I made an installation piece and left it permanently installed for them. So I was working on these Luon boards where I was laser etching some of these images into these boards. Even though those images I just showed you are rectangular, that's what they look like when they come out of that scanning electron microscope, I think that classical notion of looking through a microscope, you think of them as circular. So I changed the context by making them circular to give that sense of looking through a portal or looking through a microscope or looking through something. And so I used some of the images directly that I was using from the microscope. And then there were some that were hand-drawn from the images that I created. So there were a mixture of different kinds of images on there. Some were interpretations of things that I had seen, and some were actual physical photographs that had come from the microscope. I also printed on a million little tiny pieces of paper that I hung from the ceiling. And so these ran down the corridor of the hallway. So the pieces of Luon, they were about maybe 1.5 feet in diameter, I would say. And then the pieces of paper were maybe just 3 inches or so in diameter. So very different in scale. But as you walked down the hall, you had to navigate through these hanging pieces. They would hang to about as far as somebody's shoulder. So you had to, it wasn't just a straight walk down the hallway. You had to navigate through that space. And it changed how you actually had to maneuver through the space. You could either just walk straight through and have the paper hit you in the face, or you could find your own path through there. So it transformed the space into something else. In addition to that, I created a series of prints, just traditional prints that I had been creating. And they're almost 4 feet in width. And I worked with that size, and I worked with a certain subdued color scheme because I wanted the space itself to be ambiguous. So there are mathematical equations in these. You can see in this one in the upper left-hand corner, there's mathematical equations in them. So I'm using colors that are either natural, when you think about natural to the landscape, or natural to the human body. So that way, when you're faced with these pieces, you're not only questioning what the space is or where the space is, but then you have to question, is that space within my own body? Is that space outside me, or is that space inside my own body? And so I was taking a lot of the images from what I was looking at in the scanning electron microscope, taking them out of context and putting them in a completely different context. So you had to completely reconsider that kind of space. So then I moved on to another series. And again, I returned to the Fermi-Pasta Ulam equation. And that was just on that very introductory slide. I don't know if any of you remember that from the beginning, but that was on the introductory slide. And that is just a basic graph of what the oscillator looks like. We talked about it was that beaded chain. And so with that beaded chain, that's the basic pattern that it makes. But again, if you're thinking about these in 3 planes, if you're thinking about this movement, not just happening on one surface back and forth, but if you're thinking about it, say in a Cartesian graph, it would look something like that. So I started thinking about taking different kinds of diagrams and shifting them into this Cartesian kind of plane where you are considering that X, Y, and Z axis, where you actually have these dimensions, more than these 2 dimensions you're having to deal with. And so at the same time, I was looking at brain scans and considering that same lattice that we were looking at here, and combining the 2 so that they start to create their own lattice, or they become a lattice themselves. And so then you start to question what these things actually are. Are these cells? Are they nets that are empty? What are they? Are they something that holds something? If they hold something, are they empty? Are they cellular? Are they something much larger than that? Or are they just these 3-dimensional lattices that are based on some kind of logarithm? And so that's something that was really interesting to me as well. What I was doing was I was also thinking about